Okay, thank you. So now we have towards a practical multi-party private set union.
Thank you for the introduction. I will present our paper today about practical multi-party private set union. This is the work done with my lab mate Xavi and my supervisor Lichio, and I'm Son from Arizona State University. So the talk today will consist of 6 parts: introduction to the problem, some applications of MPSU, the challenges that we face, some related work, the construction of our protocol, and the result. First, the introduction to MPSU. So in the problem, we have multiple parties, each have a set of elements, and at the end of execution, you will have one party we label as leader to learn the union of everyone in set. The goal is to hide all the partial union between any parties and the intersection items of the party to the leader. So the leader will only learn the union at the end without any additional information. It has multiple applications. One of them is joint IP blacklist computation, where you have multiple service providers, each have a set of IP addresses that they want to block, and together they perform some service. So they want to have a union of the blacklist, and they use that to block in further services. There are also other applications as shown in this slide, ranging from private database supporting full join to distributed network monitoring or even federated learning. Even though it is very useful, it has many challenges compared to the peer two-party PSU. One is that you have to hide the source of the data point in the union. So in two-party case, if the receiver receives the union and the element in the union is not in his set, he will know that that element coming from the sender set. And it's no point to hide the source of the data. But in multi-party case, you have to hide the source because you want to prevent the partial union linkage between him and the other parties. And the second challenge is you have to hide the duplication. You have to handle the duplication of the data points. So when you have multiple senders, there are cases where the element comes from more than one sender, and you have to hide how many senders sending that element to the leader. Because of those challenges, although it is very useful, multi-party PSU is not really focused, and you see a lot of work on two-party PSU, but not multi-party PSU. Among the related work, we find there are 3 major approaches. A polynomial-based PSU, where they use homomorphic encryption, which is computationally expensive. Sorting-based PSU, they use MPC to sort the list of all elements in an MPC, and then remove duplicate elements. This is very communication expensive because you have to do the sorting. And finally, Bloom filter-based PSU, where they use local and global Bloom filter computation and later compute the union based on the filters. This is both computation and computation expensive. So we digress from all of the existing approach. We take another approach where we label one party as leaders, and the leader will expand the set by sequentially interacting with each party and accumulate the union set. We do so by using 2 building blocks. One is membership oblivious transfer, and second is oblivious shuffle and decryption. Before we come to each building block, I want to review a bit about two-party PSU reverse private membership test, which we based our approach on. So in two-party RPMT base, the receiver will learn a bit B of whether the element Y in the sender set is in its set or not. And based on this B, sender and receiver will interact in an OT to learn the final union. This bit revelation B will actually reveal the additional information. But it's okay in terms of two-party PSU because at the end you will learn such information from the result. But it's not okay in MPSU because you have to hide the partial result between the 2 parties. So we solve the problem by having secret share. So instead of the receiver learning the bit, we have the sender receiver each receive one binary share of the bit itself. And based on the binary share, they interact in the OT to have the receiver learn the correct message. And we name this as membership OT, which is short as MOT. The second building block is software encryption, where we use a traditional multi-key scheme, and with additional functionality, we name re-randomization, where we take the ciphertext and the public key, but we output the totally new ciphertext. And this new ciphertext is the same encryption of the same message, but the value is totally randomized and different from the original one. Based on such multi-key scheme, we build the shuffle and decryption, where we have each party PI come up with a random permutation PI. And first they permute the set of ciphertext they receive, and then they partially decrypt the set of the ciphertext. After that, they re-randomize the message. So at the end, we will have a new set, completely new set of ciphertext, which is one lower level in terms of partial decryption you have to do. And the order is totally different. The appearance is also totally different to the next party. So PI will forward such output to the next party. So here's an example of how it works. It's a simple example where you have three parties. P1 have a set x1, P2 have set x2 of one element, and P3 have x3 of one element. And x2 and x3 are equal to each other, and x2 is not in set x1. The first interaction is an MOT between P1 and P2. Because, so P1 as the receiver and P2 have two message, encryption of x2 and encryption of 0. Because x2 is not in the set of the first party will receive the first message, which is encryption of x2. He will expand the set of the union to accumulate the new message that he received, which is encryption of x2. This set at the end will be shuffle and decrypt, and finally reveal to the party P1 what is finally the union. At the same time, P2 and P3 also interact in an MOT. So because x3 is in the set x2, so P2 will receive encryption of 0. And after receiving this, he will re-randomize the message, send it back to P3. P3 receives this message and replace M0 with this message. And you can see in this slide, P3 now have two messages. One is the re-randomized version of encryption of 0 and encryption of 0. So both of them are encryption of 0. And even though at the end protocol, P1 and P3 interact in an MOT, and x3 is not in set x1, x1 will just learn the encryption of 0. And we add that to the final set E. And they do and at the end, P1 call decrypt a shuffle to every parties, and he will learn the decryption of E, which is x2 and 0, but in totally permuted order. And he joined that with x1 to have the final result of the union. The example is simple as it only have one element per set, that you can do couple hash and simple hash scheme previously proposed by the two works. And the protocol introduced above can be performed rather easily in the same manner. Note that we can also use batch membership tests, so in order to achieve a better complexity. So here's the performance. You can see that our protocol are the best running time in both the LAN setting and WAN setting, while we are the second best in combination cost. Thank you for your attention.
Thank you for your talk. There is an underlying assumption that there is a ground set in which all the private sets are embedded. So in that case, I wonder if you also compared your solution or the other solutions to the most naive approach in which you compute the union set by performing O. If the ground set is not too large, perhaps that simplistic approach of computing ORs is even more efficient. Have you considered that?
Yes, so in the paper we actually mentioned about the case where you have like the universe of the items and you run the PSI on that. And it is okay in terms of the universe size small, but yeah, we actually discussed it in the full paper, so you can find.
Thank you.
Yeah. So one part that I think I missed. Do you reveal the size of the data sets of individual parties?
Oh yes, so there's an assumption that the size of everyone should be the same. But if they are not the same, then you just pass in dummy values to the set.
Okay. Yeah, thanks.
We have one question online.
Who's got the other question? Or?
Sure. Does your protocol work in the malicious model or the semi-honest model? Like the shuffle and decrypt, does that have to be verifiable?
So a disclaimer that I'm not the first author, but from what I understand, it only works in semi-honest model.
Okay. And in your three-party example, each party talk to each other party. In an n-party example, is it do you still have n-squared communication, or do you just need communication like around a ring or something?
I think we need to have every party, like every pair of parties talking to each other, unfortunately.
Okay. So a lot of communication.
Thanks for the question.
Thanks.
Any other questions? No? Okay, thanks, speaker.